Data and math. Poor man's encryption. In this video, we'll implement a simplistic encryption algorithm, one that utilizes the concepts we've learned up until now. It's not meant to be perfect, or even a very good encryption algorithm, but it's a start. Later on in the video series, we'll actually break this encryption algorithm. Masking as encryption. Masking is when we combine a byte or a string of bytes on top of another stream of bytes with the exclusive OR operator to produce a masked stream. This process could be used as a type of encryption, albeit simplistic, or as a step and stage in a much more elaborate encryption algorithm. In this diagram, I only show a single byte as the mask, but the mask could be a random or pseudo-random string of integers that was the same length as the target block. That would be a little bit more comprehensive. With this specific example of a single byte mask, there are two problems that I want to improve upon with our new algorithm. 1. There's a linear relationship here. Each byte can be decrypted independent of every other byte. And 2, multiple rounds collapse into a single round, meaning if we mask, say, with byte 52 and also byte 92, it's the same as if only one round had occurred, because the 52 and the 92 combine. Of course, there's a lot more going on, and a lot that we won't get into in this simple video. This is a technique that I call functional masking. It's just about as simple. It doesn't require a finite field, but it's non-linear, and it can be run with multiple rounds. Let's look at an overview of this algorithm. First, the configuration. We'll need a unit, block, key, and the number of rounds. For example, a unit could be 1 byte, a block 16 bytes, the key 17 bytes, and the number of rounds 10. The block and the key must sum to a power of 2 plus 1. We first combine the block and the key into a single data column, and we interpret them as a function. We select a new block from the second half of this function with an offset that is randomly derived from our encryption key. We repeat this process for the number of rounds specified. Let's look at this as a diagram. We have our key and some data source, a file, a buffer, or a stream. We process one block at a time. We combine this block and our key. We functionally extend the block and the key. We then extract a block of the same size from a random offset in this functionally extended portion. This gives us a partial block, which we feed back into the process, mutating the key each iteration. After the number of rounds is accomplished, we're done. We have our encrypted block. Web demo and JavaScript API available at math.data.io.